All right, so this is U9L1, the first lesson of Unit 9, and we're talking about exponential growth. And our objective is going to be explore the exponential growth to model real-life situations. So let's start out off with the introduction to exponential equations, right? So if I give you 5 squared and ask you what that is, you'd say, oh, that's 5 times 5. That's 25. Easy stuff, right? Now, instead of that, I'm going to ask you 5 to the what power gives you 25. Well, you know this, right? Because you just did it. Because you just did x squared is equal to 25, and you know the answer to this. But this is an example of an exponential equation. And these are equations in which the variable occurs as an exponent. That means you're solving for the exponent, right? You're looking for the exponent. Like in this case, 5 to the what power is 25. And solving for this, of course, you know x is equal to 2 because 5 squared is equal to 25. Let's do another. I have 3 to the x is equal to 81. And this one, you have like, oh man, 2 times itself. Wait, 3 times itself. 3 times 3 times 3 times 3 times 3. How many times does it give you 81? And then yeah, I guess you eventually figure it out. It's, x is equal to 4 because 3 to the 4th power is 81. This equation here is slightly different, but I think it's easier. Now it's 2 to the x is equal to 2 to the 5th power. What does x have to be? Well, x has to be 5, right? Because 2 to the 5th power is obviously equal to 2 to the 5th power. So x has to be 5 for both sides of the equation to match. Your equation might get a little bit more complex like this. You have 2 to the x is minus 64 is equal to 0. And solving for it is not too hard. I just add 64 to both sides. And then 2 to the x is equal to 64. Again, you just have to try, 2 times 2 times 2 times 2. How many times does it give you 64? And x comes out to be 6 because 2 to the 6th power is 64. Here I have 2 to the 3x is equal to 64. Now I know 2 to the 6th is 64, so 3x has to be 6. Okay, that whole exponent there has to be 6, so 3x has to be equal to 6. So I solve that, x equals 2. Another one similar, I have 2 to the whole thing, x plus 1 is that exponent, right? So that x plus 1 has to be equal to 6. Then x has to be equal to 5. Now, can we find two integers that are over and under estimates of the solutions of the equation 2 to the x equals to 10? Okay, here it is. 2 to the x equals to 10. And they want you to find over and under estimates of the solution of that. What is x, basically? Now, this is really hard, right? Because 2 times itself, how many times to give you 10? That's really hard. There's really no such number that we can actually find. We can estimate it, but it's really, really hard to find exactly what it is. I don't think we can do it. Because 2 times 2 times 2 is itself, 2 times 2 to the first power is 2, 2 to the second power is 4, 2 to the third power is 8, 2 to the fourth power is 16. Okay, so what does x have to be? Now from that, I know that, well, it's 10, so it has to be between 3 and 4, right? 2 to the x is equal to 10, has to be more than 8, less than 16. So I know x is between 3 and 4. But to find exactly what it is, it's really impossible because x is really an irrational number, so there's no way for us to really find it or exactly what it is. We can estimate it though. Okay, so from that, let's use that and model real life situations here. Okay, I got a bacterial colony that starts out with one single bacterium and the population doubles every day. Okay, so this is like a pattern type of problem. So I use my table, which is what we've been doing in algebra all along, right? The left side is t, which represents time, which is basically how many days has passed. So the bacteria colony can start multiplying. Okay, on the right side, I got the number of bacteria. So I start out with 0, right? Because at the beginning, no time has passed yet. So in the beginning, the 0 day, I got 1 bacterium. Right? Now, after 1 day, it doubles, so it becomes 2. After 2 days, becomes 2 times 2, right? It doubles that. 2 times 2 is 4. 3 days is 2 times 2 times 2 is 8. Because I just got to keep multiplying by 2 because it doubles. So it means multiply by 2 one more time. So 2 times 2 times 2 times 2 gives you 16. The question is, what function p can we use to model the bacteria population on day t? One more time. What function p can we use to model the bacteria population on day t? So the function p is the function that represents the population. And t is the day. Right? What do we do with t to get p, basically? Right? So to do that, again, look back at your table, try to find a pattern. Okay? Day 1, I got 2. Day 2, I got 2 times 2, which is 2 squared. On day 3, I got 3 cubed. On day 4, I got 3 to the 4th power. So my population is 2 raised to the t, right? Look, t is 4, I raised to the 4th power. T is 3, I raised to the 3rd power. So my function is p of t is equal to 2 to the t power, right? Raised to the t power. How many days would it take for the bacteria population to reach 8? 3. We did it already. It's in the table. To reach 16, 4 days. Okay. How many days would it take for the bacteria population to reach 10? Again with this 10, we don't know, right? There's a number in between that we don't know, but we know that it's between 3 and 4 days. Okay. Now they want us to get a better estimate for t. I know it's between 3 and 4. I can estimate it to be better though. And the way I do that is I know after 3 days, it's got 8 bacteria. But 4 days is too much, right? 4 days giving 16. They want 10. Okay, let's do it. I'm going to do 3.1. And then from here, I need the help of a calculator because I need 2 raised to the 3.1 power. And the calculator tells me it's 8.574. Okay, because without the calculator, I can't do this. Okay, you got to use the calculator. And that's not close enough, right? I got to go up 3.2. So put 2 raised to the 3.2. I got 9.19. Getting closer. I want 10 though. So 3.3. There you go. 2 raised to the 3.3 is 9.849. Getting real close, right? But 3.4 might be better. Let's do that. It comes out to be 10.556. Too much. So now I know it's in between 3.3 and 3.4. You see? If I want to estimate some more, they want us to continue the squeezing process, right? So I know it's between 3.3 and 3.4. So I'm going to start with 3.3, and that's 9.849. I'm going to go up more than 3.3, but less than 3.4. It's going to be 3.31, 3.32, 3.33, like that, right? So I'm going to try that. I get 9.918. Not enough, right? Try 3.32. Maybe it's better. Well, it is better, 9.987. Maybe in 3.33 then. 3.33 happens to be over, right? So I know now it's been between 3.32 and 3.33. If I want even better, I'm going to try 3.321. And that is 9.994. That is so close. So close already. Okay. But I can go up more. 3.322, which gives me 10.001. Barely over. All right. But you guys get the process though, right? If they want more, you're going to try 3.3211, 3.3212, like that. And keep going. Okay. Now I know, though, it's between 3.321 and 3.322. Now they want this to be the nearest minute, how long it takes for it to become 10. Well, between these two numbers, I don't know which one is better, really. I'm going to take 3.321, and I'm going to convert that to how many days and hours and minute. Okay, they want the nearest minute. So 3.321 days means 3 whole days. Like that, the first 3 is the whole, and the decimal part is the partial days. So I want to take the partial part and convert that to hours. So I got to multiply by 24 hours a day. See, this is how we convert. This is dimensional analysis. So you cancel the day with the day, take the decimal, you multiply by 24. I get 7.704 hours, which means 7 whole hours. and 0.704 partial hours. And I take the decimal part and convert it to minutes. So I multiply by 60 minute over hour, and the hour cancel. I get 42.24 minutes. And the one nearest minute, so I can round that. I don't need to convert to seconds, right? Nope. So I get 3 days, 7 hours, and 42 minutes. Okay.